On August 25th, 2012, a spacecraft the size of a small car crossed a boundary no human instrument had ever touched, and the universe on the other side did not behave the way any model said it would. No probe before it had ever measured the space between stars directly. No prediction about that region had ever been tested against real data. No team of scientists had ever had to admit in print that their compass was pointing the wrong way. It is not a glitch. It is a measurement NASA has confirmed, published, and still cannot fully explain. Stay with me, because by the end of this, you'll understand exactly what was actually found. And it is stranger than the headlines let on. If you're new here, this channel covers real, verified space missions. No fiction, no filler. Subscribe if that's your thing. Let us go back to the beginning. To understand why this measurement rattled scientists, you have to understand what they expected to find, and that expectation was not a guess. By the early 2010s, physicists had a well-tested model of the heliosphere, the vast bubble of charged particles and magnetic field blown outward by the sun, encasing the entire solar system like a ship inside a bottle. Inside that bubble, the magnetic field is shaped by the sun's own rotation, spiraling outward in a predictable pattern that had been measured directly by spacecraft for decades. Outside the bubble, in true interstellar space, the magnetic field should belong to the galaxy instead, a completely different structure, generated by entirely different physics, expected to point in a noticeably different direction than the sun's field. That difference in direction was supposed to be one of the clearest signs Voyager 1 had actually made it out. Scientists even had a rough number in mind for how sharply the field should turn once the spacecraft crossed the heliopause, based on decades of remote observations and theoretical modeling of how a stellar bubble ought to sit inside the surrounding galactic field. This wasn't speculation dressed up as science. It was the standard, peer-reviewed, broadly accepted picture of the heliosphere's edge, built by serious researchers using the best data available before anyone had actually been there to check. It's worth sitting with how that older model was actually built, because none of it came from wishful thinking. For decades before Voyager 1 ever approached the heliopause, physicists tracked the solar wind using instruments in Earth orbit and on other probes throughout the solar system, measuring how its density and magnetic influence thinned the farther it traveled from the sun. From that data, they built mathematical models of a roughly bubble-shaped cavity carved into the surrounding galaxy by the outward pressure of that wind, a structure with a predictable internal magnetic geometry, spiraling outward from the sun's rotation the way water spirals from a lawn sprinkler. Outside that bubble in true interstellar space, the magnetic field was expected to belong to an entirely separate system. The ambient field of the local galaxy, shaped by ancient supernovae, and the slow drift of interstellar gas clouds over millions of years, with no obvious reason to share the sun's field orientation. Every serious researcher working on this problem before 2012 treated that separation as reasonable, testable physics. Not because they were guessing, but because it was the most consistent explanation the available indirect evidence supported. Voyager 1 reached that edge in August 2012, at a distance of about 121 astronomical units from the Sun, 121 times farther from our star than Earth itself, a distance so vast that sunlight takes roughly 17 hours just to reach the spacecraft. And the first, cleanest evidence of the crossing came in exactly the way the old models predicted. Plasma density around the spacecraft jumped by roughly 40 times. Exactly the kind of thick, telltale increase expected the moment a probe leaves the near vacuum of the heliosphere and enters the comparatively denser plasma of interstellar space. On that count, the models were right, and scientists confirmed the crossing with real confidence. But the magnetic field data told a different, much stranger story, one that took years, several published studies, and an entirely new spacecraft's worth of data before scientists could even begin to make sense of it. Here's where it gets worse before it gets better. And here is the number to hold on to. Everything that follows in this story depends on a magnetic field that simply refused to behave the way 3 decades of models said it had to. Here's the finding, stated plainly, the way NASA itself has confirmed it in published data. When Voyager 1 crossed into interstellar space, the direction of the local magnetic field barely changed at all. Scientists had expected a sharp, measurable turn. Instead, the compass needle, so to speak, held almost steady, deviating by only a small amount from the direction it had pointed while still inside the heliosphere. Read that again. The boundary between 2 entirely different physical regions of space produced almost no change in one of the most fundamental properties a physicist can measure. And it got stranger from there. Even though the field's direction barely shifted, its strength increased. The field outside the heliopause was measurably stronger than the field just inside it, which is not what a simple, clean transition into a separate galactic field should look like at all. Translate that to something you can picture. Imagine walking from your living room into your backyard and finding that your compass still points the same direction it always has, but somehow the magnetic pull on the needle has gotten noticeably harder to move, as if you'd stepped through an invisible wall into a room with its own unexpectedly powerful magnet, without the compass ever telling you which way that new magnet actually points. That is, in essence, what Voyager 1's magnetometer recorded, and it left the Voyager team publicly describing their own data as inconsistent with what other spacecraft and decades of remote observation had led them to expect. Voyager 1's own science team said as much at the time, in language unusually direct for a peer-reviewed mission update. The spacecraft's magnetometer, an instrument built to sense the strength and orientation of magnetic fields with extraordinary sensitivity, kept returning readings that simply did not fit the pre-crossing predictions, no matter how the data was reprocessed. It wasn't a single anomalous reading either. The pattern held steady across months of continuous measurement, ruling out a one-off instrument glitch or a brief, unusual disturbance passing through. This is not the language of a team that saw exactly what they predicted. In a 2013 NASA JPL release describing the anomaly, the mystery was framed directly. These observations render previous theories of the interstellar region's magnetic field questionable. Questionable is a carefully chosen word in a peer-reviewed context. It does not mean broken, and it does not mean physics has been rewritten. It means the specific model used to predict how the sun's magnetic bubble meets the galaxy's own field was, in this one crucial respect, wrong, or at minimum badly incomplete. And it got even stranger 4 years later. In 2015, University of New Hampshire physicist Nathan Schwadron and his colleagues, writing in the Astrophysical Journal Letters, went back through the Voyager 1 magnetic field data and found something else nobody had flagged at first. The field's direction, while barely different from what it had been inside the heliosphere, was actually more than 40 degrees off from the direction other spacecraft and remote observations suggested the true, undisturbed interstellar field ought to be pointing 40 degrees. Not a rounding error, not sensor noise, a genuine, sustained, unmistakable discrepancy between what one of humanity's most sophisticated instruments was measuring directly in situ and what every indirect method available to physicists on Earth said should be there. Here is where this stops being abstract. The heliosphere isn't some detached academic curiosity floating at the edge of a textbook diagram. It is the only reason Earth's surface isn't bathed in the full, unfiltered intensity of galactic cosmic radiation, a constant rain of high-energy particles from exploded stars scattered across the Milky Way. The shape, strength, and structure of the magnetic field at the exact boundary where that bubble meets the galaxy is not a side detail. It's a core input into every serious model of how much radiation shielding our solar system actually provides, how that shielding might change over time, and what any future human mission traveling beyond it would actually be flying into. If the magnetic field at that boundary behaves in ways 3 decades of models failed to predict, that's not a footnote about one spacecraft's compass reading. It's a direct signal that our understanding of the wall protecting our entire solar system was, in a real and measurable way, incomplete. Every serious proposal for sending astronauts beyond the protection of that bubble, every radiation shielding calculation, every mission duration limit built around cumulative cosmic ray exposure, ultimately traces back to models of exactly this boundary. Get the geometry of that boundary wrong, and you get the radiation exposure numbers wrong too, for missions that haven't been built yet and crews that haven't been chosen yet. But before scientists could even fully process what that magnetic field data meant, Voyager 1 itself came dangerously close to losing the ability to keep sending it back at all, and the way engineers solved that problem is, on its own, one of the more remarkable feats of long-distance improvisation in the history of spaceflight. By 2014, the Voyager team at JPL had started noticing something troubling in the spacecraft's telemetry. The small thrusters responsible for keeping Voyager 1's antenna precisely aimed at Earth, called attitude control thrusters, firing in pulses measured in milliseconds to nudge the spacecraft's orientation by fractions of a degree, were degrading. They needed more and more pulses to achieve the same tiny correction, which meant faster wear, faster fuel consumption, and a shrinking margin before the antenna could drift out of alignment entirely. For a spacecraft that depends on that narrow beam of radio contact for every single byte of data it has ever returned, that drift was not a minor maintenance issue. It was an existential one. Lose fine pointing control, and Voyager 1 doesn't stop existing. It simply stops being able to tell anyone what it finds. Losing that antenna alignment wasn't a distant theoretical risk either. Voyager 1's high-gain dish is only about 12 feet across, and at a distance measured in tens of billions of kilometers, even a fraction of a degree of pointing error can swing the narrow radio beam clean off Earth entirely, turning decades of continuous contact into permanent, unrecoverable silence in the space of one bad correction. The obvious fix should have been simple. Switch to a backup set of thrusters. Voyager 1 had 4 of them, called trajectory correction maneuver thrusters. Originally installed to make fine adjustments during the planetary flybys of Jupiter and Saturn back in 1979 and 1980, there was just one enormous problem. Those backup thrusters had not fired even once since November 8, 1980. 37 years of complete silence, sitting dormant in the near absolute zero cold of deep space, exposed to decades of radiation, with absolutely no way for engineers to physically inspect them, service them, or know for certain whether the tiny valves controlling their hydrazine fuel had corroded shut, cracked, or simply frozen. Worse, those thrusters had never been designed for this job in the first place. They were built to fire in long, continuous bursts for trajectory changes, not the ultra-short 10-millisecond pulses needed for fine antenna pointing. Nobody on the current engineering team had built them. Some of the original documentation existed only in decades-old files, written in an outdated assembler programming language that younger engineers had to essentially relearn from scratch just to understand what commands the spacecraft would actually accept. The team decided to try anyway, because the alternative, watching the primary thrusters fail with no backup plan in place, was worse. On November 28, 2017, JPL engineers sent Voyager 1 a command to fire all 4 of those 37-year dormant thrusters in a precise sequence of 10-millisecond pulses. Then came the wait. 19 hours and 35 minutes for that command to physically reach the spacecraft, and the same span again before any confirmation could possibly return. Think about what that means. Nearly a full day and a half of not knowing whether the fix had worked, whether the thrusters had fired at all, or whether they'd simply stayed silent forever, leaving the mission with no remaining option. On November 29th, the data finally arrived at a Deep Space Network antenna in Goldstone, California. The thrusters had fired perfectly, every pulse exactly as commanded, performing every bit as well as thrusters that had been in continuous use for decades. JPL propulsion engineer Todd Barber later described the mood on the team as relief, joy, and incredulity, watching decades-old hardware pick up the job as if no time had passed at all. Suzanne Dodd, the Voyager project manager, put the payoff in concrete terms. Those revived thrusters bought Voyager 1 an estimated 2 to 3 additional years of functional life, years that turned out to matter enormously, because they're a direct part of why the spacecraft was still transmitting data and still adding to the magnetic field mystery nearly a decade later. Voyager 1's mission managers described the spacecraft today in strikingly candid terms. A single-string system, meaning almost nothing left on board has a functioning backup anymore, and every remaining decision is a trade-off with no safety net behind it. Here is what is happening right now in 2026. Voyager 1 remains active, still beaming data back across a gap that keeps widening every single second. But the mission is now openly, publicly, a story of managed decline rather than fresh conquest. The spacecraft's 3 radioisotope thermoelectric generators, which convert the heat of decaying plutonium into electricity, are losing about 4 watts of power every year. A quiet, unstoppable bleed with no possible repair, since the fuel decays on its own physical clock no matter what anyone on the ground does. Of the 10 scientific instruments Voyager 1 originally carried into space, only 2 now remain switched on. The magnetometer, still recording exactly the kind of anomalous field data at the center of this story, and the plasma wave system. On February 27, 2026, during a routine maneuver, the spacecraft's power levels dropped unexpectedly, coming close enough to an automatic protective shutdown that engineers made the difficult call to act first rather than risk it. On April 17, 2026, JPL sent the command to permanently power down the low-energy charged particles instrument, one of the detectors that had helped confirm the original 2012 heliopause crossing. The mission's current plan for extending things further is something the team has nicknamed, half-jokingly, the Big Bang. A single coordinated swap of several power-hungry components for lower power alternatives, all executed at once rather than gradually. It was tested on Voyager 1's twin Voyager 2 in May and June of 2026. If that test holds, the same maneuver is planned for Voyager 1 no earlier than July of this year, which means right now as you're watching this, engineers may be in the middle of performing that exact procedure on a spacecraft 25 billion kilometers away, with a communication delay stretching into full days rather than hours. And in a few months, something happens that requires no speculation at all. A date fixed by nothing more complicated than distance and the unbreakable speed limit of light itself. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific Standard Time, Voyager 1 will be exactly 16,094,799,096 miles from Earth. That is a light day. The exact distance light itself travels, in a vacuum, across a full 24 hours. No spacecraft humanity has ever built has crossed that threshold before, and none will again for a very long time. Suzanne Dodd has described what that milestone will actually mean for the people running the mission in painfully human terms. If she sends a command and says, "Good morning, Voyager," at 8 o'clock on a Monday morning, she will not hear anything back until 8 o'clock Wednesday morning. Not because anything has failed, because that is simply, mathematically, how long it now takes for a signal to cross the distance between a machine built in 1977 and the room where people are still listening for it. Now, the honest part, because a responsible account of this story does not end with "physics has been rewritten," and anyone claiming NASA confirmed that is misrepresenting what was actually published. What NASA and its partner researchers have confirmed is narrower and in some ways more interesting. The magnetic field. Voyager 1, measured beyond the heliopause, did not match the standard model, and even years of follow-up analysis have not produced one single fully agreed-upon explanation. The 2015 Schwadron study offered one leading answer. The Voyager 1 was passing through a distorted transitional layer where the sun's own magnetic field is still gravitationally and magnetically dragging on the surrounding interstellar field, bending it out of its true, undisturbed orientation, with researchers predicting the field should gradually straighten out as the spacecraft pushes deeper into truly pristine interstellar space. But separate analysis of data from Voyager 2, which crossed its own heliopause in 2018, found something that complicates even that explanation. The interstellar magnetic field measured there came out 2 to 3 times stronger than pre-crossing models predicted, implying that interstellar particles are pressing back against our heliosphere with up to 10 times more pressure than anyone had calculated. What most people are not seeing in the sensational headlines is that scientists are not stuck between everything is normal and the laws of physics are broken. They are working carefully and openly between two real, competing, still unresolved technical explanations, a distorted transitional layer, or a fundamentally underestimated interstellar pressure environment, and neither has been fully confirmed to the exclusion of the other. Both explanations are testable. Both are grounded in real physics, and both would require updating existing models rather than discarding them outright. That distinction matters. A model being incomplete is not the same claim as a law of nature being violated, and conflating the two is exactly how a genuinely fascinating, well-documented anomaly gets flattened into a headline that oversells itself and undersells the actual science underneath it. Step back from the magnetic field numbers for a moment, and there's a bigger pattern worth sitting with. Every model humanity has ever built of the space beyond the sun's bubble was constructed indirectly, through telescopes, through theory, through careful extrapolation from measurements made safely inside the heliosphere, decades before any instrument ever physically crossed the boundary itself. Those models were not lazy or careless. They were the best anyone could do without actually being there. And Voyager 1's magnetic field data is a reminder of something that shows up again and again across the history of exploration. The gap between a good model and the truth is usually invisible right up until something crosses the threshold and reports back what's actually on the other side. This is not a story about physics being broken. It is a story about the limits of extrapolation, about how even careful, peer-reviewed, well-supported predictions can turn out to be incomplete the moment real data finally arrives from a place no one has ever stood. That is not a failure of science. It is the entire reason space agencies keep building machines that can outlast their own mission plans by 4 decades, in the hope that they'll still be transmitting the day the universe finally corrects the record. There's a reason this particular kind of story keeps getting mislabeled online as physics breaking. A genuine, hard-won scientific correction, quiet, careful, published in a journal most people will never read, doesn't generate the same reaction as a headline promising the impossible. But the real version is, if anything, more impressive than the fake one. Nobody needed to invent an alien signal or a broken law of nature to make Voyager 1's magnetic field data remarkable. The actual, verified, peer-reviewed finding that our best model of the boundary between the solar system and the galaxy was measurably wrong is already one of the most significant course corrections in modern heliophysics. It didn't need embellishing, it only needed someone to explain it accurately. There is something almost unbearably human about the fact that the instrument still catching that unresolved magnetic field signal today is being kept alive by thrusters that sat completely silent for 37 years, waiting for engineers not yet born when they were built to send them one more command. Somewhere on that same spacecraft, riding along in total silence, is a small onboard clock still counting elapsed mission time in an assembler language. Few programmers still read fluently, tracking every pulse, every course correction, every data packet sent back across a gap that now takes a full day to cross. A machine that has spent 49 years quietly proving that the universe does not stop being strange just because our models say it shouldn't be. Oh, it is still out there right now, in the cold and the dark, holding its compass steady in a field that refuses to point exactly where the textbook said it would, waiting for the next command, the next answer, the next 45-hour round trip into the silence. Every one of those round trips is, in its own quiet way, a conversation between two different eras, a command written by someone who has read decades of accumulated data the original 1977 engineers never had, answered by a machine still running the same core logic those engineers built by hand long before anyone knew what it would eventually find out there. So here's everything in one breath. In 2012, Voyager 1 crossed into interstellar space and confirmed the expected jump in plasma density, but its magnetic field data came back almost unchanged in direction and yet measurably stronger, a genuine NASA-confirmed anomaly, not a rewriting of physics, that a 2015 study partly explained as a distorted transitional layer near the heliopause. Along the way, in 2017, engineers saved the mission's ability to keep transmitting at all by successfully firing 4 backup thrusters that had sat completely silent for 37 years. Today, in 2026, only 2 of Voyager 1's original 10 instruments remain active. Power keeps draining at 4 watts a year. And in November, the spacecraft crosses the 1 light day mark from Earth. And whether that magnetic field discrepancy comes down to a distorted boundary layer or a fundamentally stronger interstellar pressure environment than anyone modeled is, right now, still not fully settled. A real open question in an active field of research, not a secret NASA is sitting on. If you want to see how this resolves, whether the Big Bang power swap keeps Voyager 1 alive past this year, or whether new data finally settles the magnetic field question one way or the other, subscribe and turn notifications on, because I'll be covering it the moment either happens. Here's the question. If a 50-year-old spacecraft's data forces scientists to admit their models were wrong, should we trust the next generation of models any more than we trusted the last one, or less? Tell me what you think in the comments. I read every single one.